Hello everyone, I hope you're doing well. In this video, we'll be solving problem 26 from chapter 5 of Introduction to Statistical Mechanics by Roger Bowley. Let's see the problem statement and we'll dive directly into the solution. The statement says, here's the statement. Let me use some pen. Consider a glass in which some fraction of atoms may occupy one of the two sides in the unit cell. These two positions give rise to two energy levels, one with energy delta I and the other with energy minus delta I. The suffix I is a label which denotes the number of the atom. Now let's understand what the statement is saying. So far what we have understood is that we have a glass that is made up of atoms, obviously, and those atoms could have two possible energies. Okay, they may have either E1 energy or E2 energy. We can just assume that one of the energy that they can have is E1 and the other they can have is E2. That's the assumption. And such configuration give rise to two energy levels, like the glass will have two energy levels, one is delta I and the other is minus delta I. That maybe will not be using later. That's just they have just defined a situation for us, and they have used some unusual symbol here to make us confused, but the problem is similar to two-level system. Okay, in two-level system we were considering only one atom that could have two possible energies, one is E and the other is minus E, and they have just used a different symbol to represent energies. This is totally similar to two-level system. Okay, and the problem that we have done before, like the problem 21, has the almost same mathematics that we'll be using here as well. Okay, just to make you comfortable with this problem. So now let's see what we have to calculate in this problem. The part A, if each atom has energy plus minus delta, just as I told you before, that one possible energy is plus delta and the other possible energy each atom could have is negative delta. So there are two possible energies. Calculate the contribution of these atoms to the heat capacity of the solid. So we have to calculate an expression for the heat capacity of a solid that is made up of such atoms that could have two possible energies. One is plus delta and the next is minus delta. In part B, they are saying if the glass is such that there is a spread in energies with values of delta I ranging uniformly from 0 to delta naught, find the temperature dependence of the heat capacity when delta naught is very much greater than kBT. Okay, in part A, we had some distinct energies that the atom could have. One is plus lambda and the second is minus lambda. But in part B, they have told us that there is a spread in energies ranging from 0 to delta naught, which means that the atom could have energies anywhere between 0 to delta naught. Okay, and they can have variety of energy values. Okay, so that is the continuous spectrum, and the atom could have any energy in between 0 to delta naught, while in part A the atom could have only two energy values, one is delta and the next is minus delta. So in both the cases we have to calculate the expression for heat capacity, but considering different energy values. In first case we have discrete values in first case we have discrete values, and in second case we have the spread in energies. So that's the difference, and I hope we have understood the problem, and understanding the problem is half the solution. And I hope you all have that map in your mind that how you are gonna get to the solution. So let's quickly get started now with the solution. And first of all, in part A, let the first energy state that it can have is plus delta, and another energy state that the system could have is minus delta. Okay, I hope that is the sign they have used. Yeah, and we know that we need to calculate heat capacity, so this is something that we need to calculate. And let us first know that what is the formula that we are gonna use to calculate heat capacity, so that we may know that what unknowns we have to get to this formula. Okay, so we know that heat capacity is given by this formula, partial E by partial T, where E is the average energy. You can use this symbol as well. Okay, that's fine as well. So that is the formula that we are gonna use, and here U bar is the average energy, and we have to calculate average energy beforehand to find out heat capacity. And the expression for the average energy will be same as we did in problem 21, where we calculated the average energy of a two-level system. The formula is same because the situation is same here. So let me call it as equation number 1, and we have to calculate it again, obviously, because I can't directly quote a formula, but you should know that that is how we are gonna do this. So we know that U bar equals, there are actually two different formulas that you can use. One is summation I PIEI, the one that we used in problem 21 as well, and another one is KBT square partial by partial T natural log of Z. Okay, that is another formula that we can use. So since I have used this formula previously as well, so I'm gonna use this one formula just to have some variety in the kind of formulas that we can use. This one formula has been used in the problem 21 as well, so you can use this as well. It will give us the same result, and this one will give us the same result as well. So it's totally up to you what formula you wanna follow. Okay, so I'm gonna use this one in this problem, natural log of C. For that purpose we should know what Z is, okay, which is the partition function. Partition function of a two-level system is given by e to the power minus delta by kT kBT plus e to the power minus delta by kBT, because we have two energies here, one is plus delta and another is minus delta. So we can this is the partition function of a single atom. Not all of the atoms are considered here. This is for the single atom, and each atom could have either negative E energy or positive E energy. So that is the partition function we have, and we can write it to be equals to 2 cos hyperbolic of delta by kBT. Okay, because we have this formula for cos hyperbolic of x, that is equals to e to the power x plus e to the power minus x divided by 2. Okay, we have the same situation here. Here x is delta by kBT, and there is 2 missing, so we can take 2 to the other side. So it's 2 cos hyperbolic of x equals e to the power x plus e to the power minus x. So we can replace it with this. It will make this differentiation way easier. Okay, that is why I'm doing it. So that is Z, and we can insert this right back into equation number 2 to get the internal energy. So we can do here kBT square partial by partial T natural log of Z, this is Z, 2 cos hyperbolic delta by kBT. Okay, now let's apply the derivative on here, and this is the derivative of natural log of a quantity. So let me write a general formula for the derivatives of logarithm, so that you may know how to apply the formula. So if we have d by dx of natural log of y, for example, so then derivative of natural log of y would be equals to 1 over y. Okay, this thing will appear in the denominator. There will be reciprocal of this term dot derivative of this term with respect to this one thing. Okay, so that's how the derivatives of logarithms work. Okay, so we are gonna do this here. We write it the same way. kbt square remains the same, and we have 1 over 2 cos hyperbolic delta by kbt dot partial by partial t of 2 cos hyperbolic delta by kbt. Since t2 is constant, so it will be we can take it outside of this differentiation, so this 2 and 2 cancels out, and we are left with, let's see what we are left with. So we have here kbt square divided by cos hyperbolic of delta by kbt, partial derivative with respect to temperature, cos hyperbolic of delta by kbt. Now we need to solve this differentiation. And what is the derivative of cos hyperbolic of angle? Derivative of cos hyperbolic of x is sine hyperbolic of x dot derivative of its angle. Angle is x, so derivative of angle. Okay, cos changes into sine and derivative of its angle. So let's do that here. In simple trigonometry, if we had cos x, then its derivative is minus sine x. Okay, but in hyperbolic functions, cos hyperbolic of x changes into sine hyperbolic of x. That's the difference you have to keep in mind. So cos hyperbolic of delta by kbt, and here cos changes into sine hyperbolic of delta by kbt dot derivative of its angle. That's the operator, derivative operator of angle. Angle is delta by kbt. And let's simplify it. Kbt square sine hyperbolic of delta by kbt, and here it's cos hyperbolic delta by kbt. Sine over cos is tan, so it's tan hyperbolic of delta by kbt. Then we have partial derivative over this quantity, and it's the property of partial derivatives that it only considers those terms as variable which contains this thing. So only temperature will be taken as variable, and rest of all other things will be treated as constant. So delta by kb will come out of the differentiation, and we will have derivative over 1 over t only, and derivative of 1 over t is minus 1 over t squared. It is similar as partial by partial x of 1 over x, which is minus 1 over x squared. Just replace x with t, so it's that kbt squared tan hyperbolic of delta by kbt dot delta by kb, and here we'll write minus 1 over t square. T square cancels out, kb cancels out, minus delta could be written at the starting point, then tan hyperbolic of delta by kbt. If you recall problem 21, we got the same average energy for the two level system. It was just E here in place of delta. We have just used some other symbol for energy. That's the only difference. Rest of all is same. So, and we have seen that the solution was really simple, and we have got the average energy, but we wanted heat capacity, which is simply, we know that heat capacity, we have written its formula at the start. So CV equals partial u bar by partial t. CV equals partial by partial t, let's put the value here, minus delta tan hyperbolic of delta by kbt. So Cv equals minus delta could be taken out because that doesn't contain temperature, tan hyperbolic of delta by kBt. Now what's the derivative of tan hyperbolic delta by kBt? I'm calling delta by kBt as angle. Okay, so derivative of tan hyperbolic of angle is equals to secant hyperbolic square of angle dot derivative of its angle. Okay, simple as that. So let me write here partial by partial x of secant square y, let's say. Oh, sorry. Partial by partial x of tan hyperbolic of y, let's say we have that situation. So it would be equals to secant hyperbolic square y. This changes into secant hyperbolic square with the same angle dot derivative of angle. That's the rule. Always we'll take the derivative of angle and one trigonometric function changes into other. So tan hyperbolic changes into secant hyperbolic square. So let's do that. Minus delta secant hyperbolic square delta by kBt. Okay, there is square on the hyperbolic and derivative of its angle. Cv minus delta secant square hyperbolic delta by kBt could be written as cos hyperbolic square delta by kBt in the denominator, because we know that secant is equals to 1 over cos. So that's how I have written it. Delta by kb partial by partial t or 1 over t is again minus 1 over t square. So let's simplify here. It's minus delta, it's minus becomes plus delta square, and it's Cv equals delta square by kBt square, and we can write cos hyperbolic square delta by kBt. That's the formula so far. That's the expression for the heat capacity of such a configuration in terms of temperature. Okay, and if there are capital N number of atoms in the glass or the solid that I have shown, so heat capacity would be simply equals to, you write here this formula again, times N. Okay, that is the heat capacity of the solid. Alright, while this would have been the expression of heat capacity for the single atom in terms of single atom, but to constitute the contribution by all of the atoms, so we just simply multiply it with capital N. Okay. In part B, we can see here that we have a spread of energies, which means that there is a uniform distribution of energies, which is generally represented by delta I sign, and it is varying from 0 to delta naught. Alright, and we have to find out the heat capacity expression under this approximation. Alright, let's see how we can do that, and you must be expecting integration in that case, because let me tell you that whenever there is some discrete functions or discrete values like plus delta and minus delta, there is discrete summation that we represent by that summation sign that you probably see. Let me draw it here. It's like that. Okay, whenever there is discrete summation, we use this thing, okay, which involves the discrete summation, like we add each term separately, 1 plus 2 plus 3 plus 4, for example, like that. Or in our case, we saw that we calculated the partition function like that by kt and plus adding each value individually. This is what we call as discrete summation, and then we have continuous summation that is done through integration, because integration involves that and takes into account the complexities involved in continuous summation. Okay, so we'll be using integration here. How we'll be doing that? Let's see. Let we have a uniform distribution in energy delta I, all right, ranging from 0 to delta naught. Okay, the partition function for such a configuration of atoms is given by the partition function of a single atom with possible energies that range from 0 to delta naught, because we have a continuous range of energies that atom could have. So in that case, the partition function of single atom becomes different than that which we calculated in part 1. Okay, so in part 1 we had only two possible energies that the atom could have, plus delta and minus delta, but here this atom could have any energy in between 0 to delta naught. Okay, so in that case the partition function for this system becomes different, and how we'll be doing it, it's like that is equals to the partition function of a discrete case, okay, as a function of delta I, as we can see in the start of the statement that this statement is true for both of these parts. So the atom could have delta I distribution as, okay, as a general distribution, or minus delta I as general distribution. So there are two possible kinds of distribution the atom could have. One is plus delta I and the other is minus delta I. So we have to incorporate both of these possibilities into this situation, and that delta I could range from 0 to delta naught. That's something different. Okay, so z of delta I, then d, we have to integrate it. Okay, and we have, like, we'll average it out over all the possible energies. Okay, and we divide it with this. If you know, then you know that how to calculate the averages using integration formula, and mathematically we write equal sign parallel to this separation division line that separates the division. So you should write z here, because I was unsure about where I'm gonna write. So z should be equals to like that, and it should be parallel to this line above and below this term. Okay, so this is the averaging of partition function of single atom over the range 0 to delta naught. Okay, we'll average it out, we'll simplify it, and we'll get the result. So let's see that how we are gonna do this. So 0 to delta naught, in place of z of delta I, we'll write the partition function with discrete summation of two possible distributions that the atom could have. One is minus delta I by kt plus e to the power minus into minus delta I by kt. Okay, there are the two possibilities here, and divided by, here we have only one as the integrand, so its integration is simply delta naught. Oh, sorry, it's delta I here, because we are doing it over I, and so it's I over there. Okay, that was a mistake. So I here, and limit of integration 0 to delta naught. You can refer to this general rule where we have like this, the integration by dx, when we do not have any other number and we have only differential over here, then its integration is simply that number, that variable, so it's x, and limit of integration applies accordingly, whatever the case is. So we can see here that its integration is simply that, and z equals 0 to delta naught, and we have e to the power minus delta I by kt plus e to the power delta I plus delta I by kt, because minus minus becomes plus, delta I, divided by limit of integration. In place of delta I, we write upper limit, which is delta naught, minus in place of this variable we write 0. So that is how you put limit of integration, and you will get delta naught minus 0 is actually delta naught, and we'll get delta naught in denominator, which we can write like that. Okay, and we have this integration now. It's not a part of this integration, so it could be written outside, and we have this term here, which we can write in terms of hyperbolic functions. If you recall that what that thing is equals to, well, this is the form that we have got so far, and if we recall, we can express this summation of two exponentials with equal power. That's the exponent, and they both have same exponent but different in sign. It has positive exponent, it has the same exponent but negative, and bases are same. So we can express them in terms of hyperbolic function, and we know that that cos hyperbolic of x equals e to the power x plus e to the power minus x divided by 2. That is cos hyperbolic of x, while sine hyperbolic of x equals e to the power x minus e to the power minus x divided by 2. So whenever it's negative in here, we can use sine hyperbolic of x. Whenever it's positive in there, we can use cos hyperbolic of x. Since we have e to the power x plus e to the power minus x form here, 2 is extra, we can take 2 being divided here to there, which is being multiplied. So z would be equals to 1 over delta naught 0 to delta naught 2 here into cos hyperbolic of delta I by kt, positive sign, okay, keep that in mind, d delta I. So this 2 can be taken out because it's a constant. 2 by delta naught 0 to delta naught cos hyperbolic of delta I by kt d delta I. Alright, so now we have to simply integrate it, and it's a really simple integration. We have cos hyperbolic of this angle, and it is being integrated over delta I. So delta I am just mixing the delta I symbols here. I am using this triangle and delta here, so they are same, okay, please don't confuse it to be different, they are same, okay. I'll make sure that I'm using this inverted triangle later forever. So the integration of cos hyperbolic of angle is cos changes into sine hyperbolic of delta I by kt, and this whole quantity is divided by the derivative of its angle. So we have partial by partial I delta I, because integration is done over delta I, that is why the division by derivative would be with respect to delta I. So derivative of angle is delta I by kt. Whenever you are integrating or differentiating, the inner term's derivative is always being multiplied if it's differentiation, and it will be divided if it's integration, okay. So keep that in mind, don't be confused, and we'll have limit of integration from 0 to delta naught z equals 2 by delta naught, and sine hyperbolic of delta I by kt. We'll apply the limit of integration later when we will calculate the denominator. So 1 over kt is since constant, so it will come out, and partial delta I by partial delta I is left behind, which is equals to 1. Limit of integration 0 to delta naught, 1 over kt could be taken outside. 1 over kt is in denominator, so it jumps to the numerator here, okay. It's 1 over kt in denominator, so it becomes if you are confused, so you can use this technique that 1 divided by 1 over kt, what it is equals to 1 divided by 1 over kt. You can write it like that, and when divide sign changes into multiplication, this jumps, you know, the order changes, and we have 1 multiply kt. I hope you got it. This is from the high school, secondary school mathematics, that if 1 divided by 1 by kt, so it changes in multiplication sign, so this kt, it's inverted, so it becomes like that right here. And by delta naught and upper limit minus lower limit, upper limit sine hyperbolic of delta naught by kt, in place of delta I will write delta naught. whoever the variable was, in place of that variable you'll put the limit of integration. Okay, since the variable here was delta I, that is why we are putting in place of delta I. So wherever the delta I is, you will put upper limit minus wherever what I'm doing, wherever the delta I is, put 0. So sine hyperbolic of 0 is 0. This is equals to 0, so it's sine hyperbolic of delta naught by kt, and this is the partition function so far that we have got. Now we need to calculate average energy, and after calculating average energy we'll be able to calculate the heat capacity. And after calculating, after all of these calculation, after we are done with it, we will apply the limit, the approximation that is given in the question. So internal average energy, we know that average energy is given by, you can write that statement, it's equals to kbt square. Kb is Boltzmann constant, simply k, so I'll use kt square. Okay, partial by partial t of natural log of z. Let's do that. Kt square, putting the values, partial by partial t natural log of z. What's z? 2kt by delta naught sine hyperbolic of delta naught by kt. Okay, that is using bracket to show that it's whole thing inside the natural log. Okay, let me write it in next page. U bar equals kb t square partial by partial t natural log of 2k by delta naught, I'm writing it separately, and t sine hyperbolic of delta naught by kt. Okay, so yeah, that is it. kbt square. Now it's the property of natural logarithms that whatever is inside being multiplied, we can separate the natural log on all of them such that it will be there, all of those terms which are being multiplied in the numerator will be added, while those which are in the denominator will be subtracted. Okay, so we have natural log of 2k, I am writing it separately, plus natural log of t. Okay, they are being multiplied with each other, then plus natural log of this term which is sine hyperbolic of delta naught by kt, that's a whole one term. Okay, that's a whole one term and it has this angle, minus natural log of delta naught. Okay, you can see here those which were in the denominator, their natural logarithm is being subtracted, while the others which were in numerator, they are being added. It's the property of natural logarithm that if it's like that, xy divided by z, you can write it as natural log of x plus natural log of y minus natural log of z. Okay, that's the property that we have used here, and it will help us to simplify, because when we'll apply the partial by partial t on all of them separately, since it doesn't contain temperature, it becomes 0. It doesn't contain temperature, it will become 0 as well when you'll apply partial by partial t on both of these, but these ones has t in them, so their partial by partial t will not be 0, and we can proceed simply by applying on those that really matters. So we are left with this, and let us simplify it. Partial by partial t of natural log of t. Now let's see what is the general formula for finding out the derivative of natural logarithms or logarithms in general. So when we have partial by partial x, for example, of natural log of y, I'm calling it as inner term, so its derivative is equals to 1 over inner term, derivative of inner term with respect to what was being applied. Okay, the same will appear here. So here the inner term is t, other than natural log, the thing we'll call it as inner term. So t is inner term, 1 over inner term dot derivative of inner term which is t with respect to this. Here similarly 1 over inner term is sine hyperbolic of delta naught by kt dot derivative of inner term. Inner term is sine hyperbolic of delta naught by kt. Same here, okay. Let's simplify further. It's 1 over t, this becomes 1, partial t by partial t is 1 over sine hyperbolic delta naught by kt dot. Now let's find out the derivative of sine hyperbolic delta naught by kt. Sine changes into cos hyperbolic delta naught by kt after differentiation. As I told you earlier, always the inner term's derivative will be taken. Here inner term is the angle, derivative of inner term, which is delta naught by kt. Here the variable is t, not delta naught. Keep that in mind. And we have plus, this is cos hyperbolic and this is sine. Cos over sine is what it is, cot hyperbolic delta naught by kt. Sine over cos is tan, while cos over sine is cot. Then partial by partial t on delta naught by kt. Here t is the variable, so delta naught by k will be taken out and we can write them here, delta naught by k, and partial by partial t will be applied on 1 over t, and kbt squared 1 over t plus delta naught by k cot hyperbolic delta naught by kt into partial by partial t of 1 over t is minus 1 over t squared. So we know that partial by partial x of 1 over x is equals to minus 1 over x squared. Okay, that's how I have written this. Then we have kbt squared 1 over t minus, this plus and minus becomes minus, delta naught by kt squared cot hyperbolic delta naught by kt. Okay, now we can multiply kbt squared inside, so we may get some simplified form, kbt squared by t minus kt squared. It's kb and k is same, I'm just kt square cancels out, this t and one of the t cancels out, and we have kb or kt minus delta naught cot hyperbolic of delta naught by kt. This is average energy so far. Now let's find out the heat capacity. The problem is almost done. Okay, we have just reached the end. We know that the heat capacity is given by partial u by partial t. So let's insert the values here. We know that u is kt minus delta naught cot hyperbolic of delta naught by kt. Alright, now let's apply the partial by partial t on both of these terms because it's being multiplied. So delta naught will come outside because it doesn't contain t. Partial derivatives only applies on the term with respect to which the derivatives is being applied. K will come outside, partial t by partial t will be left, which is 1 minus delta naught. Derivative of cot is minus cosecant hyperbolic square. Okay, cot changes into cosecant square. Hyperbolic, so it's hyperbolic square delta naught by kt dot derivative of inner term, which is delta naught by kt. We haven't applied any limits so far. Okay, so minus minus plus delta naught cosecant square cosecant hyperbolic square delta naught by kt. Partial by partial t will only be applied on t, so delta naught by k will come outside and we have partial by partial t of 1 over t, the same thing that we did before. Delta naught by k could be written here, delta naught becomes delta naught square by k. This is an angle of this term, so that's not outside of it, you can't multiply it with this. Okay, keep that differentiation in mind, that this is a separate thing. And delta naught square by k cosecant hyperbolic square delta naught by kt. Then we have partial by partial t of 1 over t, which is equals to minus 1 over t squared, as we saw before. K minus plus minus delta naught squared by kt squared cosecant hyperbolic squared delta naught by kt. That is the heat capacity so far. Finally, we have reached a point where we are 2 steps away from the solution, and here we are going to apply the approximation. We had delta naught very much greater than kT. Okay, this is the approximation, which means delta naught by kT is very much greater than 1. We can take kT, it's being multiplied here to the other side, that is allowed in inequalities as well. Okay, so we can write this, and here we have this situation which could be approximated using this thing, and for that purpose we should know that, let's say we are doing it in rough work, okay, or you can do it in neat work as well. We have cosecant hyperbolic delta naught by kt to be equals to 1 over sine hyperbolic delta naught by kt. We know that cosecant is inverse of sine, okay, and we know these formulas as well, that sine hyperbolic of delta naught by kt equals e to the power positive delta naught by kt minus e to the power negative delta naught by kt divided by 2. Okay, so since it's 1 over this, so the 1 over sine hyperbolic of delta naught by kt would be equals to 2 over e to the power delta naught by kt minus e to the power minus delta naught by kt. So we can write this thing right here. So cosecant hyperbolic delta naught by kt is equals to 2 divided by e to the power delta naught by kt minus e to the power minus delta naught by kt. Okay, now since we have delta naught by kt very much greater than 1, which means that e to the power minus delta naught by kt, e to the power with negative power in a greater number, if we have e to the power a greater number, then this value is very much less than 1. Okay, and in comparison to this value is very small. Okay, it's just like if we add 2000 with, let's say, 0.2. Okay, that doesn't bring much of the difference. So we can neglect this term under this approximation, and this goes to 0, and we can have cosecant hyperbolic delta naught by kt to be equals to 2 over e to the power delta naught by kt. Okay, so we can this is cosecant hyperbolic delta naught by kt, so we'll square both sides to get the value of squared one, because that is what we have here. Hence we'll square both of these sides, so taking square and square will appear here, and cosecant hyperbolic square delta naught, okay, by kt equals 2 square is 4 divided by e to the power 2 delta naught by kt. Okay, so when we take squares of exponentials, they actually gets multiplied because they're already powers, so they multiply with each other. Okay, never ever confuse it with the thing that you may write it like that, delta naught square by k square t square. No, that's wrong. You can't do that. That's not what it is. Okay, because that's already a exponent, so taking square which means another power is being multiplied, so 2 is being multiplied to delta naught by kt, that is it. So that is something that we have got. We can take this e to the power 2 delta naught by kt in the numerator, so it becomes minus 2 delta naught by kt. We can put this value right back into this equation to get the final results. So CV equals, you will write it like what we are putting it back, k minus delta naught square by kt squared. In place of cosecant hyperbolic square delta naught by kt, I am writing 4 e to the power minus 2 delta naught by kt. Okay, and here we can see that this is a significant term, and k is equals to 1.38 multiplied 10 to the power minus 23. That is a really small number, and we can neglect as compared to this number. Okay, so CV is equals to delta naught square mod of this value. So we are taking positive values. Negative heat capacity doesn't make any sense. That is why we are only taking the positive quantity. So delta naught square by kt square for e to the power minus 2 delta naught by kt. That is the overall temperature dependent heat capacity expression when delta naught is very much greater than kT. So this is the final result, and we can see here that CV varies with the inverse of square of temperature and this exponential factor. So both of these co-determines the expression of heat capacity at low temperature. So that is the expression. I hope you got it. Like, share and subscribe. Goodbye.